That's our imaging spectrometer. As it flies over a particular target, it actually gimbals so that it slows down the apparent motion of the ground track to get better spatial resolution on the planet. In the yellow boxes are what our high-resolution imager typically takes. And in the white lines is outlined the swath width of our context imager, which has an 18-mile wide swath as it's flying along, and yet it's able to resolve things that where a single spot is on the size of 20 feet or so. Also there you see a yellow ellipse, or almost a circle. That is what we expect the landing air ellipse for the Mars Science Laboratory to be when it lands on Mars in 2011. By air ellipse, we mean we aim for a certain point, but we could land anywhere in that ellipse due to uncertainties about navigation, due to the changing atmosphere as we fly down through it on a parachute, and then land down on the planet. So you can see that we're able to cover these landing air ellipses, and that means that many of the images that we've taken, and MRO has taken over 10,000 of these high spatial resolution images down on the surface. Each of those is a potential place for a future lander, including MSL, to go. Now, we've gone through a process of narrowing down those candidate landing sites, and we'll show some of those here at the end of the talk. But we've gone through about a list of 36 or so, down to 4 final candidates. Because MSL was slipped from launching in 2009 to launching in 2011, we have an opportunity to perhaps add 1 or 2 more. And if so, MRO will go back and finish the reconnaissance for that to ensure not only is that a scientifically interesting place to go, but it is a safe place for the lander to go. This particular area also has a diverse composition and stratigraphy to it. And we're going to take a look at that in a little more detail here. So if we go to the next step. Here we're looking at a crater that is in that scene, a little bit to the northwest of that scene. And what you see here are, in the different colors, are different periods in Mars history. The bluish areas have clay materials that are there. Those materials were formed through the action of water. The reddish areas are a mineral called olivine. In the presence of water, it alters to something else. So the fact that it is there and exposed here says at the time that that material was in place, that there wasn't water activity at the surface altering it. Above that, in the crater there and eroded away, is the basalt, probably formed when the impact crater itself formed here. We're going to zoom into this area because it's interesting for another reason. There's a particular mineral that we've been looking for on Mars called carbonate. And what we'll see in the next one is look for the greenish areas because those are more indicative of where the carbonates are. So let's go to the video, please. There's a diversion here. I need to tell you that elsewhere on the planet there are other layers that we're going to be looking at. But for this point, let's zoom in again to this crater. You'll recognize our basalt lava-filled crater here and where it's been eroded away. And what we're going to do is zoom across this landscape. And you see, again, in false color here, differences in the mineral deposits. The ones that are colored green are the ones that are the carbonates. Now, why is carbonate interesting? Well, first of all, it's a carbon-bearing mineral. So that means that there are places on Mars where you can preserve evidence of life. If it ever existed on the planet, there could be places where there could be fossilized materials or other biosignatures of past life if it existed in these areas. And looking at this diverse landscape, though, you can see that there's been a lot of action and activity since the period of where these minerals were emplaced. In some cases, they're the youngest part of the surface, they're superimposed, but that may also be because they've been eroded, the material that once covered them is eroded away, exposing them down on the surface. So these are the clues that we're looking for when we go to our future landing sites. And all of the MSL candidate landing sites have evidence of these aqueous minerals, although not of carbonates per se, but of aqueous minerals indicating both compositionally and structurally that water was active at those sites. Returning to what I sometimes call the Spanish Steps, you notice this very regular pattern of terrain here. There's a set of layers, and then there's kind of a packet of layers. And as you go from one to the other, there's the suggestion here that there's something that has been episodically controlling the deposition of these sediments on Mars. They were turned to rock. They were later exposed by erosion. We're going to fly into this scene a little more, And this is the one video that does have vertical exaggeration to be able to highlight the steps that are in there. I think it's 4-to-1, vertical over the horizontal. So let's go to the video, and we'll fly into the scene, and you'll get an idea of where it is on Mars. We do this because, you know, the postage stamp size of the high-resolution things, it's a little hard to see the scale. You start from space, you zoom in on, you'll see the character of what we had in our previous resolution of data, and then you're going to what we now have at the much higher spatial resolutions. So looking across this landscape, you can see a very complicated, complex pattern, but punctuated by these very regular layers. Now, what might be happening here with these? And we'll talk a little bit more about that. But there is another place on the planet that also has layers, and those are the polar regions of Mars. So let's go to the next time step, please. Each of those layers is several yards thick. The stacks are tens of yards, and the whole domain could be as much as a mile thick. And we're seeing it exposed as it's being eroded away down into it. So here was a place, a very regular place of activity in the deposition of those materials and such. Next time step, please. One of the ways that we think those steps may have been formed is by the fact that Mars has, it has not only a day that's much like our own, just 40 minutes longer, so it rapidly rotates around its rotation axis, but that axis also tilts, just like the Earth does, and we see seasons. But what we're going to do here is we're going to take a look again. We're back into this terrain. And you'll see by that regularity of pattern, there are certain frequencies that can be extracted just by the thickness of the layers themselves. We can compare that frequency of occurrence of those patterns to the forcing patterns. And by forcing, what do I mean? This is the amount of sunlight that the polar regions receive. And why is that important? Well, right now there's a block of ice, a mile deep at the North Polar Cap. As the planet tilts more towards the sun, that means that its season will be longer, the sunlight will be more intense at those high latitudes. That water vapor can go away and go elsewhere on the planet, and then in other periods it'll be colder. And so you may move water from high latitudes to low latitudes in a cyclic process. On the next slide, the next video here, we're showing you an artist's conception of what this tilt looks like. And the motion here looks a little ragged, but remember that what you're actually looking at is the variation over millions of years. But we're still looking at recent geologic time, the last several million years of Mars. And in fact, on the graph here, what we're looking at is 5 million years before present and what 5 million years after will be. The tilt, that is what produces the seasons. And we have that here on Earth, of course, too. But the variation of the Earth's rotation axis, that tilt, only varies by a couple of degrees, and yet we think that's enough to be involved in the ice ages that form and come on the Earth. On Mars, that variation is much larger, tens of degrees, and that's partly because Mars is a lumpier planet, partly because it's closer to Jupiter, which is the big bully of the solar system, it being the largest planet in the solar system, which gives a stronger tug and a stronger variation to this. And as you saw in that artist's conception, the idea is that ice moves across the planet from the polar regions to lower latitudes where it captures dust as well, mixed into it, and that could form the layers. The layers that we were looking at may be much older than what we're able to produce today with these kinds of changes in the forcing and the rotation axis. So a question is just what is the age of that? Right now our way of counting and dating the surfaces of Mars is to look at the number of craters that are on there. But if the materials, those steps had been covered and then later exposed by erosion, there's a whole period of history and crater count that our ages just will give this to be a much younger surface than it may actually be. And so it may actually have been part of a surface water deposition or a groundwater activity producing those. Let's go to the next video. Now, I said elsewhere on the planet that there are layers, and we have a way of looking at the layers not only as they're exposed at the